Bonjour tout le monde, re-bienvenue. Hello again, everybody. So for the third conference of the day, it's a pleasure for me to introduce you Foutse, which is a full professor at Polytechnique Montréal and also a shareholder of FQR Ivado on software assurance quality on AI application. And okay, and he is also a member of the academic. There is a feedback. Ok, Foutse, je pense qu'on va couper le son.
Moi, j'ai pas de retour.
T'as pas de retour, okay. So, okay, I'm sorry, there is some feedback in my ear. So it's a pleasure to present you Foutse, that is one of my partner in research that is doing something that I really like. Give me the point of view of software engineering for this AI certification project. Foutse, you have the la parole.
Thank you very much, Francois, for the very kind, generous introduction. Thank you, everyone, for attending, for the opportunity to allow me to discuss with you some of the work that we'll be doing to try to help this new technology gets to maturity. So since the morning, we've been discussing about how AI is likely to transform mobility and all the challenges that comes around ensuring that we can actually deliver safe products using this technology. In this talk, I want to work you on an aspect that is sometimes overlooked, which is the software that you have to produce to be able to deploy these models in production. So briefly, as you know, AI is getting everywhere, right? It's poised to transform mobility. There were some early forecasts that in the very near future, we will have self-driving car being a reality in our lifetime. We're still making progress to other directions. It's having tremendous impact already on healthcare, right? And we're using it in all the communication devices that we are having nowadays in our homes. And it's making some inroads in the aerospace industry, right? And we're having a variety of projects in which we're trying to build strong foundation to ensure that we can reap the benefit of machine learning in a safe way to bring intelligence to mobility and to aerospace. So you may be not, I mean, at this point, you'll be convinced about the challenge, some of the challenges around modeling with machine learning, but I want to walk you toward the software aspect, right? So why is AI, in particular machine learning or deep learning, so different from what we used to do, right? Why all the focus on the software perspective of the additional challenges that this technology is bringing? So traditionally, which is what I call here in my talk, software 1.0, when we design a system, a software system in particular, we start by deciding about the requirement, right? We decide on what we want our system to produce as services, right? We describe clearly what's our intent, and then we encode the rules that will govern the behavior of our system, right? Which as a result makes us to allow us to have a pretty much clear view of the flow information in the programs, which make it more easier to reason about the behavior of the program and to test the program eventually. While with machine learning and deep learning and other learned technology in general, things are a bit different, right? So instead of encoding the algorithm, the state, writing the rules that govern the behavior, we program the computer to actually generate these rules, right? So we infer the behavior from data. So which result in a shift in paradigm, which have been coined in recent years as software 2.0. So we have been facing a new reality in which we have much little control on what is the behavior that is encoded in the program than we used to. As a result of this, it's more challenging more difficult to reason on the behavior of the system, and to ensure that we have guarantees that what is inferred from the data is actually robust, safe, sound, and that we could actually ensure full traceability about what the system is doing over its evolution. So how do we build a model? Allow me to walk you quickly about the different steps. I'm sure everyone in the room is aware of these different steps that are required to produce a machine learning model to put in production. But one aspect that I want to raise your awareness, it's the amount of instruction that you have to write and program code that you have to generate. In a certification context, as we are in the aerospace, all of these artifacts have to be certified to some extent, right? You have to be able to prove a clear traceability all through these phases, and we have to be able to demonstrate that we understand exactly what will be the behavior of all those statements, and that we can be sure that when they will be deployed in production, there won't be adverse effects. So typically when you build a model, what you do is, well, you set up the environment, right? So you have to configure the environment, decide on what are the libraries that you'll be using to train the model. This requires generating programs, right? So you're writing programs to do that, and then you collect the data. Right? Everything depends on what is in the data, and the data comes over a diversity of formats. So you collect data from different sources, which require you to script this process. So you write code for that. Once you have the data, you have to process the data. Right? So the data is usually not in a perfect shape for learning. So we have to apply a set of transformation, which is implementing codes to clean up the data and to process it. Once we have it, we have to encode the logic that we want to use to infer patterns from the data. So we have to implement the training programs. We decide on the architecture of our program, what are the hyperparameters, what kind of activation we want to use, depending on how we want the learning to proceed, which all these require writing a set of instructions, right? Which has to be accurate, has to be tractable, has to be traceable. Once we have this, we have to train the models. We generate some insights from the data. We have to evaluate our model. Traditionally, we have a set of data that we left out, and then we want to see how our model performs on the data. We have some validation data allowing us to tune the model, which is a process that is also scripted. And once we reach that process, usually we have to introspect and observe what's the behavior of the model is before we can push this to productions, right? So before we can actually deploy a machine learning model to be able to generate insights, we write a lot of code. So it's actually a continuous process that goes from model building to the deployment. And as the model is deployed on the field, through the evolution of the systems, everyone is aware of what happened is that the distribution will shift. So we'll have to retrain the model, and this process has to be continually being updated. So in a safety critical context, we have to ensure that all through this process, we can actually provide a clear guarantee that we have sound data all through the process, that the model behave as it is expected to behave, and that the code that we're producing, I insist on the code here because usually it's often overlooked, that the code that we produce, it's free from defects, right? It's free from errors. So the burden is harder. As any traditional program, machine learning program fails, right? But they fail in a different way, which make it more challenging for testing and certification purposes. Compared to traditional software system, actually the space of failure for machine learning-based system are wider because we can have errors in the model. Most of the time we're discussing about how on the specification issues and problem in the model. But on top of that, we actually have implementation issues. Even if the logic by which we want to infer behavior from the data is sound, if it's encoded in an unsound ways with defect, it will result in a faulty program. Right? It will result in a program that won't be safe. We also have issues with data. The quality of the data is key, right? We have to decide on what's the best way to clean the data, and then we have to be able to test for the quality of this data. So the dimension space of issues that we have to handle when we're in the context of machine learning system, even more critical in the context of machine learning system in a safety critical domain, is much more broad. The community have started looking into these directions strongly, and then there is a state of testing strategy that have been proposed over the years now. So we have to test for different properties. We have to test at a unit level. We have to test whenever we do integrations of different components. We have to test for things like fairness. We have to test for bias. We have to ensure that all the structure all through the process are sound and that we can actually repeat the process and provide stronger guarantee. So compared to traditional system, the maintainability issues of machine learning it's also broader because of this tight dependence on data. Right? The dependence of the model of the data prevents from enforcing strong abstraction boundary on the program, which make it more prone actually to complexity creeping in the programs and also to technical debt. So it's much more challenging actually to maintain those systems. And this is one of the aspects that I really want to shed light. It's something that I've been trying to ensure that we don't overlook when we're trying to provide a certified end-to-end pipeline for bringing ML system in production. So to comply with these certification standards, we need to develop tools and techniques that allow to ensure reliability in the system. And this is what I want to share a bit with you. So in the rest of my talk, I hope I have convinced you at this point that the model is not the only target that we have to spend our effort on. We have to look at the code that we generate to produce the model. So in this rest of the talk, I will walk you through 3 techniques that we actually propose to help with that. So the first techniques allow to detect for issue in the training program. So our target here, we focus on the training programs, the set of instruction that you're writing to instruct the machine to generate that algorithm, that model that we actually use for inference. We propose a different set of techniques. So I've picked 3 of them for this talk. The first is a static technique. Why static testing technique is potentially very useful for this? Because it's cheaper, right? You can actually track errors earlier in the process without the need to run the code. So you can actually run an abstraction of your program. And with a set of validation rules, you can detect issues in the program. This allows for early debugging of this program before we actually have a model. Because one thing that is tricky, and you're all aware with machine learning, is that we have silent failures. You can have an underspecified model, but you're still having a model, right? So it's very hard to actually ensure that this is the best that you will have and that you will actually be able to guarantee safety on it. So these techniques allow for static testing. We build another set of techniques for dynamic testing. So at this point, we pass the first static checks of issues through program analysis. And then we have the training program. We're in the training process where we actually start inferring regular structure from the data epochs after epochs. And at these steps, we're actually monitoring, as we do for traditional software debugging. So we monitor the flows, control flow of the training program to detect for issues. Right? So we build a set of techniques to allow to support this aspect of the development. The last technique that I hope I will have the time to walk you through is a testing technique for the model. So once you have trained the model and then you obtain the model ready for inference, you actually have to ensure that this model is robust. Right? So you want to be able to test for potential issues, misbehavior in the model. To do that, we usually, traditionally in software testing, we generate a set of input test data sets that we will use to exercise the decision logic of the model to allow us to identify areas where the model is actually easily sent off track. This way, we can actually improve the training to increase the robustness of the model. And there are different techniques that have been proposed to actually generate these inputs data sets to allow for this robustness testing. And I will present you briefly one of the techniques that we propose and explain why we went that way. Okay, so static testing. What do we do with static testing? So we have a program. Again, I emphasize the focus here is the training program. So we have a set of instructions that we have encoded to instruct the machine to actually learn. To actually generate a model. By doing static testing, at this point, we want to capture issues in that set of program, right? So to do that, we need to identify what kind of issues we want to focus on. Right? Then we need to build a taxonomy of faults. So the first step that we took to design this technique is that we built a taxonomy of faults that occur generally in machine learning training programs. To do that, we study a set of programs that have been written using 3 very popular libraries, PyTorch, Keras, and TensorFlow. And we rely on platforms like GitHub, which is actually the largest platform in the world currently hosting programs, including machine learning programs. So we extracted programs from these platforms. And also we consult Stack Overflow, which is actually a question and answer where people actually discuss issues about their training programs. This allowed us to extract a set of potential issues that occur on those programs and to classify these issues based on the root cause of the failures. Right? So an example of issues is, you can see here, is an incompatibility, for example, between the self and the activations, like in a specific context. So this is a violation of good practices for CNNs. And through this process, we build a set of rules that actually capture on the specification issues and errors in the models. So things like reshaped data detections, retentions, unnecessary activation removals, and so on. So we have categorized this, and this process was actually expanded by some colleagues recently in the community. And then we now have a taxonomy of faults that occur on deep learning programs. So this taxonomy characterizes all types of issues to some extent that you can actually experience when you're building a deep learning program. Why is this interesting? Is that because now that we have a taxonomy, we can actually reason about the behavior of that program. To do that, we need a representation of the program. So we propose a Metamodel, which allows us to have an abstract representation of the training program. So this is a brief representation of the Metamodel as a type graph. You can have the detail if you follow on our papers, it's online. So with this type graph, we actually specify transformation rules. So for each type of failures that we identify in the training programs, we specify transformation rules as a grass transformation rules that we will use actually to detect occurrence of the errors on the program. So how does all this works in practice? Whenever you have your training programs, using our tool, you can extract an abstract representation of your training program, which is a model, which is specified following the Metamodel that we introduced. And then we're using the taxonomy of failures that occur on those programs. We actually have an engines that allow to do verifications. So you can actually verify that your model is complying and that it's free taxonomy. And as the result of this, you have a list of issues that you can actually debug early on in the process of the model. So this gives you like a bird view of the process, high-level process of how the approach works. It's a model-based verification techniques. We call it Neuralink. It's open source and it's free to use. We assess the effectiveness of this technique on a set of programs, which are real programs that actually have been written to train deep learning models. And we found that it can successfully detect a lot of errors. So this can be actually a tool that helps toward improving the reliability of ML-based systems. And it's very efficient, which is one of the strong suits of static testing techniques, because we don't need to run the system, so we're saving in execution time. Now, the second technique that I wanted to briefly discuss, it's dynamic testing techniques. So at the static time, we cannot capture all the issues in the program because there are some dynamic dependencies that only reveal when you start running the program. So we also build a technique that allows us to introspect the evolution states of a training program to identify issues related to the training. What are those issues? So how does this work? Similar to the previous techniques, we have the program that we monitor. Our tools here, it's an extension of the libraries, of TensorFlow libraries, that allow us to hook in the states of the training program and monitor the behavior of the program. So we will monitor the evolution of different states of different variables, and then we will detect issues. What can we check? So by monitoring the evolution of the training process, we can identify problems such as untrained parameters, poor weight initializations. Right? Let me go very quickly. And you can have activations related issues. I'm sure many of you are aware of those issues. So these are issues that we encoded. So for each issue, we design a verification rules that allow us, by comparing distributions of values through the evolution of the training process, we can actually detect cases of these issues crippling in the training program. So we can detect when we have date review, when we have diverging gradient and so on. So this technique is implemented in the tool as well, which we call the deep checker. It's an extension, it's a library that you can use. And what it allows us to do, it's allow us to actually monitor the training process of deep learning based programs. So this works for deep learning programs currently, but can be extended to other machine learning systems. And by monitoring session after session, you can actually detect problems in the program. Right? So you have training issues and then you can get some warning. So we also evaluate this on real system. And you can actually capture a lot of problems that are at the root cause under specification. As you all are aware, this is actually a big problem with machine learning modeling currently. So looking at the software aspect of the problem, you can actually catch some of these issues early on before you actually build them on.
10 minutes left, Foutse.
Yes. Okay, I think will be good. So you can capture coding mistakes. We can capture misconfiguration problems. So this is good, right? You will say. But we didn't stop there. So now that we have the model, you also need to test the model, right? So assuming you went through the static checking, the dynamic checking, and then you have a model that's produced, you need to test for whether or not this model is robust enough. How you do this? Well, you generate input test data. So here we took a parallel from traditional software testing. So traditional software testing, we have the control flow of the graph. We want to make sure during testing that we cover as much as possible. How do we cover this? We have to generate data that will be fed through the programs, and then we observe. For this, we need an oracle. How do we do it with deep neural network? Well, we use what's the concept of neural coverage, right? That have been, it's kind of an anomaly for code coverage, and it's adapted for neural network. So we need an oracle. For machine learning, we don't have oracle, so which is a problem. We actually have to couple more with confidential correctness issues, and labeling is expensive, right? So you need proxy techniques. So to solve this problem, we rely on metamorphic testing, right? Which is a technique that allows us to exploit the properties of the data. Right? So we have a data, we know that after transforming this data, the label should not change. Right? Assuming we have a cat during the winter, if we change the background and we're in the summer, it should still remain a cat, right? So we leverage this property to actually generate input test case data. So there are different techniques that are proposed in the literature for the same problem, but the key here is the lack of diversity. So the goal was to improve diversity. And how do we improve diversity? We rely on search-based techniques. Right? So with search-based techniques, you can actually evolve a population of solution, which allow you to improve diversity in your generated test case data. So neural coverage is the level of activation of neuron. The intuition here is that if we observe the decision of the model enough through a process in which we activated a significant amount of neuron, our confidence in the reliability of the output should increase. Right? So we want to generate as much testing data that we need to activate as much of these neurons during the decision of the model. So to do that, we use search-based techniques, which allow us to transform metamorphic relations. So we start from a set, we build this is the overall structure of our techniques, but briefly, what it's important is that we start from a set of transformations, which is a metamorphic transformation, like brightness, contrast, translation, scaling, shearing, for example. And then we will evolve this transformation using genetic techniques or metamorphic techniques by controlling that the semantic of the images, in this case, we were in context of computer visions, are preserved. So by evolving these techniques, we actually able to generate additional input data. The key fitness function that we use is maximizing the coverage. So whenever we generate new data, we want to generate data that's increase the coverage with respect to what we already have in the previous generation of the population. So we proceed with these techniques, and we actually evaluate with a variety of meta heuristic, and it worked pretty well. Right? Compared to Foutse, which is fuzzy. TensorFuse, which is actually built by Google Brain, we actually could detect more issues in the models compared to this running with these techniques. So roughly, I wanted to raise your awareness about the software part, the source code part of the problem, and how we can actually leverage techniques that we have been developing software engineering for over the years to adapt to this problem to increase guarantee that we can actually provide. And in a certification context where we have to ensure that every statement that is used to produce the system is actually accounted for the behavior, and that we can ensure full traceability over the evolution of the system. This kind of techniques, I believe, part of the solution. And so we developed a set of techniques, static, dynamic, and also test case input generation techniques. I hope I have a few time to get some questions. I hope I wasn't too...
Yeah, we have five minutes extra because we start 5 minutes later. So you can go on. I hope it will work.
Yeah, so I'm happy to take any questions that you have.
Oh, so Foutse, are you still there? Yeah. So we have until...
I'm here. I'm happy to take questions.
Okay, so if you have some questions, please, you have to put them on the chat of the main session. So, okay, see, in the meantime, I have a very difficult question for you. You want to make some certification of the many steps of the creation of your AI program, but for that you are using Keras or PyTorch or others underlying software that are not certified at all. So what are you doing with this problem?
Yeah, so this is a very, very good problem. So very good question. So these techniques we build based on open source program that we available. But the process by which we actually develop these techniques is fully transferable in this context in which we have a tighter control on what everything that is used to produce the software. So in the case of, let's say, a safety critical context in which programs are not created using TensorFlow or Keras and other libraries, in the first step, we will need to generate a taxonomy of failures that are related to the tools that we use in that context. So here, TensorFlow and Keras is just a case study at this point. It's because it's open source, and then we have access to enough artifacts to test the technique. But the process of generating the verification approach can be replicated, not without some challenges, but it can be replicated in the context in which we're using a different set of tools to build a program. What is important is to understand at this point that the program that you created to generate the model also has to be certified and sure for correctness. And to do that, what we're proposing is to do a program analysis of that program, which is, in our case, is a Python program. It could be written in different languages. And then we have tools that we already built for traditional software that we can actually adapt to detect issues in those programs and to increase our safety.
That will include PyTorch, basically.
It could be include PyTorch if the program is built using PyTorch. If it's built using TensorFlow or MindSpot or any other new libraries that is popping up, the same approach can be applied to. It's really a program analysis driven approach. So we shift a bit the focus from the model, which is a byproduct of this process, to actually the program that is written to generate the model. And what we're interested in is to detect issues in that program and ensure that we can increase our guarantee on the reliability of that program before even starting worrying about the eventual on the performance of our generated model.
I see.
If you have a faulty program, it doesn't matter what you generate, you won't get a good model at the
end. And okay, I see. It's clear, I think. So I will ask you the same question I asked to Guillaume at in the first conference. So now you have a method that try to overcome all the difficulty by defining a huge batch of tests that will basically cover, in your sense, all the possibilities. An aircraft, when the aircraft is flying, is confronted with a reality. So there's a lot of situations that cannot happen in reality, right? For example, there is no teleportation of the plane from one place to the other, and so on. And so these ideas are important if we want to make a set of tests that is only related to what will happen in practice and not what can be in a science fiction situation. So how do you think about this fact, how to include knowledge of the physics, basically, of the reality?
That's a very, very good question. I think it applies on the third approach where we already have the model. And then
we have 1 minute. 1 minute.
Yeah, we have to test for the robustness of the model. So good thing here is that we're relying on what we call metamorphic transformations. Right? So metamorphic transformation is a set of techniques that allow us to start from a seed of input data and to evolve this population to generate additional interesting data. And this evolution process, the transformation process, can be controlled. So currently, I haven't presented here, but we have work where we're actually leveraging the knowledge of the domain to actually fine tune the generation of this additional input data. So you can actually encode the physics, the domain knowledge of the context in which the model will be deployed to ensure that the additional test case data that you're generating are actually the most relevant for the property that you want to ensure in the system. So this can be encoded in the technique, and it's also part of ongoing work that we're doing with some of the partners in actually in this space, in the aerospace industry.
So, very good. Yeah. We have some, it seems that we have 4 minutes left. I don't know how it happens, but we have until 11:05. If the reality is what happened in the website for MobiliT.AI, and I have a question from Sandrine. So how do you counter the lack of diversity of data? Could you create a synthetic data set, for instance, with a Cartesian product of the different feature and look at how the model reacts on its synthetic set? So this is really related of my question. How can you deal with unreal data and put it in reality? Because it's a good idea. It's to have a synthetic data generator, right? But this is not exactly the same situation. So how will you deal if the training set is on synthetic data?
Yeah, so the way we actually, so with the metamorphic approach is we start with a seed of data and we want to evolve them to cover as much as possible the diverse space. But then we use a meta-heuristic approach, which is a search-based approach, which means we're guided by a fitness functions. So the key idea here is how you decide what is your fitness function to prioritize what kind of offsprings you want to keep in the testing process. And the work that we're exploring currently is how to use knowledge, domain knowledge, and rule. For example, in the case of the project that I cannot tell more, but it's in the context in which we're testing something that is, for which we had a simulated versions on which we know the physics law that govern the problems. And what we do in that case is that we adapt the rules. So what we expect because we know the law of the physics, we ensure that whenever we generate a new input, we actually stressing those properties with the new input. So there is a ways to actually leverage that type of information to guide and fine tune the generation process of the additional input testing data. It is still not perfect but it's a way of combining the symbolic knowledge that we have with this data-driven process, right? So it's an avenue that we pursue, and the early results show that you can generate interesting things, but still we're still far from perfect coverage in a way.
Okay, so I think we have to cut it here. I will thank you, and I will say to all the people that this is one of the richness of the DEAL project, to have people from software engineering having a software engineering point of view of AI that will work with us, me instead, which is more a theoretician of learning theory. I think we have something interesting to push, and so I thank you, Foutse, for that, and
thank you.
Hoping that everybody has find it interesting. Of course, Foutse is.
I'm around all the day.
He remains available if you have offline questions to add and stuff like that.
And so I'm happy to share the papers as well. Thank you.